All right, folks, we have Glen Gibb from Intel, who has worked on Tofino hardware for several years, and then the Intel Tofino compiler for several years as well. He's going to give us a talk on the Intel Tofino compiler, which, as early announced today, will be open source soon.
All right, thanks for the introduction there. I've got a lot of material today to go through, so I'm actually going to talk very quickly and skip over a few slides along the way. In fact, skipping over this one. Now, Deb's already stolen my thunder. The big announcement, of course, is that we're open sourcing the Tofino compiler and the rest of the components. So you can kind of consider today's talk as a bit of a primer for when you get that code and you want to sort of understand the basics of how things are structured there. And so here's the outline for my talk today. I'm going to start talking, give an overview of the Tofino architecture, have a quick mid-end / back-end tour, talk about the custom IR nodes, talk about a couple of information objects that we have, PHP info and PHP field, introduce the resource allocation algorithms, and then go through backtracking. So with that, let me start with the Tofino architecture. So up there on the screen is the protocol independent switch architecture. And I'm sure you've all seen variations of this diagram before. But on the left-hand side, we have the programmable parsers. We then have a series of match action units, both in ingress and egress. There's some buffering sitting between the ingress and egress. And then, of course, there's packets coming out on the right-hand side. And that maps onto the Tofino architecture as follows. So in this diagram, I think my mouse pointer is working. Okay, on the lower left side here, we've got the max and some ingress buffering. The ingress buffering feeds into a series of ingress parsers, which basically corresponds to the programmable parser on the top left. That then feeds to a series of match action unit stages. So in Tofino 1, there's 12 stages. From those stages, we then go to an ingress deparser. We then have our queues and our packet buffers. These loop back around, come back to a series of egress parsers. Again, from the egress parsers, we go to our match action unit stages, finally to an egress deparser, and then the max, where obviously our packets come out of the Tofino chip. Now, just a couple of things I'll highlight on this before I move on. These match action unit stages, they're actually shared between ingress and egress. And this, in the diagram here, the light and blue rectangles here represent something called a packet header vector. And again, that's shared between ingress and egress. And just a couple of important things there. So the match action units, each match action unit implements multiple logical tables. As I said, they're shared between ingress and egress. And there's a lot of allocatable resources in each one. So things like TCAMs, SRAMs, ALUs, crossbars, etc. The packet header vector, it's a very wide vector. It's at least 4 kilobits wide. Slightly wider in Tofino 2, and that's partitioned into a series of 8, 16, and 32-bit containers. And as I said on the previous slide, it's shared between ingress and egress. And the packet header vector basically flows from the parser all the way through the MAU stages and then to the deparser. And I'm just going to introduce something called the packet occupancy vector. It's the only time I'm going to talk about it today. But basically, it's a bit vector that indicates which headers are present in the packet. And that's also stored in the packet header vector. So with that, let me start the mid-end / back-end tour. So the mid-end is very similar to the PSA switch mid-end. This image on the right-hand side is just the diff against that particular back-end, particular mid-end. Some of the things that are unique to the Tofino mid-end. Okay, first of all, we have some specializations of some existing P4 classes. So things like check unsupported, type checking, and a few other things like that. We have Tofino customizations. And I should just add BFN. The BFN prefix is for Barefoot Networks, which is where Tofino originally came from. We check design pattern adherence a little bit and make recommendations when design patterns aren't followed. This is just to make it easier for the compiler to map things down onto the Tofino hardware. There's a little bit of architecture translation. So some custom IR nodes are introduced here. There's normalization across Tofino, the Tofino 1 and Tofino 2 native architecture, plus the V1 model. A little bit of simplification, so some cast eliminations, some control rewrites. And then there's a little bit of var-bit processing as well. So basically verifying that the usages are supported and desugaring those usages. So replacing var bits with small fixed length chunks of fields. And there's a bunch of other minor things as well that I won't go over. All right, sitting between the mid end and the back end, there's actually a pass called bridged packing. And basically what this does is it packs any metadata that has to be passed from the ingress to the egress side. And the reason it does this is that that metadata actually gets deparsed on the ingress side, prepended to the packet, flows through the packet buffers as some extra data on the packet, and then gets parsed on the egress side. So, we have to pack it so that we have things like multiple bytes. Sometimes there might be some alignment issues we have to deal with, etc. And then the other thing that that bridge packing does is it translates more IR nodes to Tofino versions. And then backend, okay, there's a lot that backend does. Three key things it does. First of all, instruction selection. So basically choosing which ALU instructions to execute for each P4 primitive. It does the PHV allocation. Think of that as register allocation in the traditional compiler. And then table allocation, basically choosing where to place each P4 table in the MAU pipeline. And there's a bunch of smaller features as well. Things like aliasing, so detecting when two fields are equivalent and only allocating once instead of doing two allocations for that. Metadata initialization, and this is for backwards compatibility with the old Tofino compiler. We collect pragmas for use for things like constraint enforcement. There's parser IR lowering, which I'll touch on in a slide or two, and a number of other smaller little features. So now, moving on to Tofino IR nodes, I'm not going to go over all of them, but I'm just going to touch on a few here. And the reason that we have these IR nodes is to better represent the underlying hardware. And if you're familiar at all with the open source IR, a lot of these classes will seem somewhat familiar, or at least you'll be able to understand why they exist. So first batch here, we've got TNA parser, which is a subclass of P4 parser. And then we've got TNA control and TNA deparser, which are subclasses of P4 control. And you can see there that we've added a few properties, so things like the thread, because it could be ingress or egress. We've got a pipe name. So in Tofino 1, there's 4 independent pipes. We can have either all pipes sharing the same configuration or individual pipes having different configurations. And then there's TNA params mapped there. And that's basically just mapping the parameter names that are used in the P4 program to a set of canonical names, just to make it easier for the compiler to see what parameter is what. All right, a few more IR nodes I'm going to introduce. So we have this thing called BFN unit, which is the base class for a lot of other subclasses. One example subclass is this MAU table. You can see properties there, again, things like the thread. We have gateway information, and gateways, think of these as small little tables that effectively implement conditional statements that control whether a table loop executes or not. So it might be something like, if is IPv4, then execute this table. We've got stage information, we've got a logical ID. Here, we also map back to the original P4 table object, and you can see there's other properties there as well that I'm not going to go over. We then also have a series of attached memories. So, I'm mentioning before, we've got the SRAMs and the TCAMs. The SRAMs can implement a lot of different types of data structures. So it could be like, we could be using it for action data, counters, meters, etc. So each of those is a subclass of the attached memory. And you can see on the left-hand side that one of the properties of the table is a set of attached memories. There's lots of other BFN unit subclasses as well that I'm not going to touch on. And then a couple of other things I'll just quickly mention. We have something called MAU instruction, which is a subclass of BFN primitive. And this is really representing the ALU instructions as opposed to the P4 primitives. We have a set of parser classes. So we've got parser state, and extract. These are field representation versions of a lot of the parser infrastructure, because typically when you write a P4 parser, you would work at the header level. You might say extract IPv4. And so the compiler converts this into extract IPv4.ihl.length, et cetera, et cetera. And then we have lowered versions of these as well, which instead of working at the field level, actually work at the container level. And yeah, there's a few other classes, but if you have familiarity with the P4, standard P4 classes, then a lot of these things will seem somewhat familiar. All right, next we have a related set of classes or objects, PHP info and PHP field. So PHP info basically collects and accumulates information about all of the PHP back storage in your program. So this is basically like fields and metadata. It provides a set of iterators to iterate over those fields if you need to do something to all the fields. And then it has a bunch of several query interfaces for getting information about specific fields. So we have a method there, for instance, field. You can give it a name, you can give it an expression, and it will return a P4 field object that has more detailed information about that field. And this P4 info is populated by a class called collect PHP info. And so then the individual fields themselves, these PHP field objects, they basically they collect all the information about a single field. So things like the name and the ID, etc. But there's also like properties as well, which would be examples of which could be, is this metadata? Is it a field? Is it a packet occupancy vector? Is this field, should it be solitary? So basically, can we not pack anything else with it? Does it need to be mutually exclusive? A few other things like that. Eventually, the PHP field objects also contain alignment constraints. Maybe we need to put this particular field in bits 7 through 4 of a particular container. It will eventually contain the PHP container allocation once the PHP allocation is completed. Contains things like alias information and a few other things as well. And then the PHP field objects have some higher order functions to iterate over and process the allocations. So we can like iterate through all the bytes belonging to a field, and we can also iterate through the slices of a field. So maybe at some point, instead of taking the whole IPv4 address, we just need like the low 8 bits of it. And so that would show up as a slice that's used within the program. All right, and I know I'm going through things very quickly here. And now I'm going to quickly talk about the resource allocation. So we've got two different resource allocation strategies. We've got the classic allocation strategy that's been there for a long time, where we start by allocating PHVs, and then we perform table allocation afterwards. And then more recently, there's been an experimental alt PHP allocation strategy that's been added, where basically the ordering is flipped. So we do table allocation first, followed by PHP allocation. And that's not strictly true. We actually do like a pre-PHP allocation round where we assume infinite resources, but that's basically just to use as a starting point. So how do these two algorithms work? Well, first of all, for PHP allocation, we begin by collecting constraints and then creating clusters. And then this clustering, if you're not, since nobody here is probably familiar with the internal details of the Tofino chip, basically that PHP space, or that PHP vector that I talked about with containers inside of it, those containers are broken down into a collection of groups, and I think it's roughly 16 containers in a group. But we have a constraint that typically for an MAU instruction, both the operands and the target field must all belong to the same group. And so we've got to be a little bit careful when we allocate fields to containers to make sure that effectively all the fields that interact with one another through instructions belong to the same group within the PHP. And then operands also typically need to have the same alignment. But once we've created all these clusters, then we have this nested sort of iteration loop here, where we go through the clusters that we've created, and then for each cluster, we go through all of the possible container groups. And then within the cluster, we go through all of the allocated slice, or all of the identified potential slices in that. And for each, within that, we basically try to perform allocation for the particular slice within the container group we're looking at. And assuming that we get at least one allocation, then we choose the best allocation and commit that allocation. And in terms of trying the different allocations, we're basically trying each container within a group at each valid alignment for that particular slice. And so, we run this process. It takes a while because you've got to go through all of these clusters, container groups, etc. And at the end, if it's unplaced clusters, then we fail. Okay, and in doing so, we actually do multiple tries, and there's several different search and scoring strategies, but conceptually, this is the process that we go through. Resource allocation kind of looks somewhat similar if you squint a little bit. Here, I've got an infinite while loop where I begin by getting all of the placeable tables due to dependencies. And really what this means is, imagine that we have a table sequence A followed by B, and assume that table B uses as an input something that was produced by table A. In this case, we can't place table B until we've placed table A because we need the result that's produced by table A. So at any point in time, we get all of the currently placeable tables. If we don't have any, we stop. Otherwise, we iterate through those tables, and we try to find an allocation for each of those tables. And we record what each of those allocations is, and then we choose the best allocation and place that best allocation. And sorry, when I say we choose the best allocation, we choose one table that has scored the highest, or we commit that. And then we repeat that process over and over until hopefully all of the tables are placed. And of course, if we have unplaced tables, then we fail. I guess the one thing I want to highlight here, in terms of finding the allocation and choosing the best allocation, we tend to prefer tables in longer sequences. And the reason for this, we've got a fixed number of stages in the chip. So it makes sense to place the longest sequences first, and then fill in any gaps with shorter sequences. We also prefer placing larger tables over smaller tables. The reason being that within a single MAU stage, I think we're limited to 16 or 32 tables. But there's some fixed number of tables you can put in a stage. So again, it makes sense to place the larger ones first and then fill in the gaps with the smaller ones. Otherwise, you potentially end up with unused resources in a stage. And in general, we try to pack things earlier in the pipeline to leave later stages if possible. And the actual process, of course, is more complex. We do some internal and external backtracking. And so the last thing I really want to talk about is backtracking. Basically, during the table allocation and the PHP allocation, if we get ourselves into a state where we can't make forward progress, we go back to an earlier state and try again. So within table placement, we use both local and global backtracking. The local backtracking, as we're going through, we record partial placements. When we detect that we're placing a table beyond the end of the MAU stages, we go back to an earlier point and make a different decision about which table you want to place next. And then we limit the number of backtrack attempts just so that this process doesn't go on forever. And then we also have global backtracking, where we go from table placement back to PHP allocation and try a different PHP allocation. And when we do this, we pass information back via this MAU backtrack object that basically says, hey, this is what we did in table allocation. So then PHP allocation can use that information to try to get a better allocation. And so I've rushed through things very quickly there, and I know there's a lot to digest, but in summary, the compiler is being open source soon. There are some custom IR nodes. I talked about both PHP info and PHP field as useful classes to get information about fields and their allocations. I touched on the two major allocation problems that we have, and then of course talked about backtracking. And I just want to thank everybody who worked on the Tofino compiler. It's been a huge team effort. And it hasn't just been the compiler engineers, there's also been lots of people who have contributed in terms of like bug reports or feature requests and other things like that. So thank you. And if there's any questions?
Yeah. Hi. So this is a very general question. So
Sure.
has the Tofino team provided feedback to the open source P4 compiler team? Have you had discussions on how the P4 compiler ecosystem should evolve? And could you, elaborate on that? Thanks.
Yeah, well, so in terms of that, I would say certainly at the beginning, the Tofino compiler team and the P4 open source team were basically the same entity. Because mostly, certainly the basis for the open P4 compiler came out of the Tofino compiler development efforts. A number of the people who, particularly people like, say, Mihai, for example, was at Barefoot to begin with. And so, he contributed a lot. And a lot of other people too who worked on open source compiler contributed. I guess also I would say, these days, we still try to contribute as much as we can. We certainly still contribute like bug fixes. What else? More recently, we contributed a def use pass, so identifying defs and uses for variables. And then we also try to participate in all of the P4 language working group meetings and architecture meetings and things like that. So we're certainly trying to contribute back to the open source community and help guide things in the right direction.
Okay, thanks.
Thank you.